Yeah, good morning, everybody. I hope everything's fine with my screen sharing. Today I'm supposed to talk about partial differential equations. And I have uploaded the slides. Or I will work with the Jupyter notebook. I've uploaded it and updated it a little bit. What you see, what you can download at the Canvas server is not exactly what I will show you today, but for most parts. But I made a few add-ons this morning. But I will upload the updated version as well. I also consider having everything in one side, so we will solve the things of the tutorials inside this file. So after the tutorials, I will upload the updated file. Okay, so let me also open the Slack channel such that I have a view of the if there are questions on the chat. Yeah. And please let me know in the chat when everything, whether there is a problem. I've discussed if you want to use make use of the Python code that is embedded in the Jupyter notebook, you should be able to run this, and yeah, you may want to replace matplotlib widget with matplotlib inline. We have discussed this on Tuesday. Yeah? So let me run this. And I'm supposed to talk about partial differential equations. So first, before we look into what we can do with partial differential equations, let me tell you what is a partial differential equation. I guess most of you here will know and may have some need for it, but nevertheless, I want to start with the easy stuff, with the definition, yeah, for completeness. So a differential equation is a differential for an unknown function of several, more than one independent variable, and it's partial because it takes derivatives, partial derivatives. That means derivatives with respect to more than one independent variable. And an example is an equation like this. You see here's an index. The index means that we have a derivative with respect to this independent variable. So let's say we have a function of three independent variables, x, y, z, and a partial differential equation is a differential equation that takes derivatives with respect to more than one of these independent variables. No? In this case, you see there's a derivative with respect to x. So this is indicated by this. It's a shorthand form because you don't want to write these partial differentiation operators every time. In particular, if you are working with LaTeX or another word processor, this is a convenient form to abbreviate it. Yeah? And my convention is the closer the index is to the function, the earlier you take the derivative. Yeah? So this would mean in my notation that you first take the derivative with respect to x, and then you take the derivative with respect to y of the result. Actually, we assume in most cases, we will talk a little bit about continuity in the nonlinear case, but in most cases we assume that u is a continuously differentiable function with respect to every variable, and this means that that's the theorem of Schwarz, that the order doesn't matter. So if in this case, if the function behaves nicely, which means it's continuously differentiable twice, then the order doesn't matter. Yeah, so it doesn't matter whether you first take the derivative with respect to x and then to y, or first to y and then to x. That's the same thing. Yeah, that's the case in there are pathological functions that do not fulfill this, but usually when you get acquainted with these functions, you will know what will happen. So all of these nice functions, e to the polynomial of sine of something, so every combination of continuous function fulfills this nice condition. Yeah. So this is a partial differential equation, and yesterday you learned about ordinary differential equations, and in order to find a unique solution, you have to assume boundary or initial conditions, yeah, or a combination of both, boundary conditions and or initial conditions. Initial or end conditions. When we talk about initial conditions, we usually think of one of the variables as a time variable. And the spatial variables, we would rather call them boundary conditions. Yeah, but it depends a little bit on the application. Yeah, so this should answer the question, what is a partial differential equation? So it looks like this. Yeah, and so this is a non-linear, non-homogeneous equation, but you don't have to care. I will show you a few examples. And now the next good question is, what can we use this stuff for? And actually, partial differential equations are everywhere. So there is a huge amount of applications, and they are still an area of active research. So quite a lot of interesting questions on partial differential equations are still unsolved. I will come back to that in a minute. But I just show you a few examples. Where can we find differential equations? So for instance, we can find it in electrostatics or electrodynamics, because Maxwell equations, this is are of electrodynamics. These is a set of a system of linear partial differential equations. The propagation of sound and light is governed by a partial differential equation, so the so-called wave equation. The propagation of matter or heat in diffusive processes, or heat propagation, this is governed by the so-called diffusion equation. I will show you how to derive it or make it plausible. Questions of fluid dynamics are governed by partial differential equations. So again, a system of partial differential equations called the Navier-Stokes equations. And I gave you a link because why is this interesting? This should just emphasize that this is a very open area of research and there are still unsolved problems. And you may have heard about the Millennium Prize problems. Yeah, so that's I give you the link. So if you can find something out about the Navier, funny enough, they are featured here on the homepage of the Clare Mathematics Institute. Yeah, so this is a foundation dedicated to increase and disseminate mathematical knowledge, and as a kind of motivation, they have singled out 7 interesting problems. Yes, so the here there are some of them, and you see Navier-Stokes is one of them, of these so-called millennium problems, Navier-Stokes equation. And for all of these millennium problems, if you solve them, so if you can get serious information about the Navier-Stokes equation, I would be happy if I made the one who gets the Millennium Prize, if I would have motivated one of you and who will later get the Millennium Prize. Yeah, so what is this prize? Yeah, you get $1 million for it if you solve this problem. Yes, and you will get a position wherever you want. As on top, yeah, I'm sure. And if you are young enough, you will get a Fields Medal on top. Yes, so it's nice. Look it up. There's the official problem description, every information that you know. Yeah? And of these Millennium problems, only one has been solved. That's the Poincaré conjecture. That has been solved by a Russian mathematician called Perelman. Maybe you have heard about it. And the crazy thing is he rejected this prize. He said, no, I've solved the problem, that's enough. I don't want to have the money. And he also was young enough to get the Fields Medal, and he didn't take this too, as far as I know. So the kind of Nobel Prize of mathematics. Yes, so you see, this is one of maybe the most prominent partial differential equation, or set of partial differential equations, but there are more. No? So there are problems in general relativity, Einstein's field equation for the gravitational field. So how the space is curved, that's Einstein's field equation. No? So having as solutions, for instance, gravitational waves. And you know that gravitation, or you certainly have heard that gravitational waves are a very, very active field of research. Quantum mechanics, so the famous Schrödinger equation, is a partial differential equation, which looks very similar for a free particle to the diffusion equation that we will see in a minute. In financial engineering, you have the Black-Scholes equation. In civil engineering, so basically, this is very similar to the diffusion equation, but in a completely different context. There you don't talk about diffusion of matter or heat propagation, but the interpretation is the price of an option. But the underlying phenomena are very similar, or the mathematics is very similar. Yeah, and in civil engineering, you have a structural analysis problem, flow transport problems. So in a way, it's a mixture of many of these fields. Huh? Not so much general relativity, but many of the other equations. So let me have a brief look at the chat, whether anything came up so far. I think this is not for me. Okay. So as a brief motivation, let me just derive or make plausible how such a differential equation can come up. And the motivation is the so-called continuity equation. I will discuss it only for a one-dimensional case. So we have one time dimension and a space dimension. And we think about the concentration of a substance at position x at time t. Yeah? We have one spatial dimension. Let me put something on the whiteboard. Sorry, I have to make sure that this works. Oh, sorry about that. Sorry. I have to confirm that I can use that. We should be ready to go. Okay. Yes. So hope you see the whiteboard and you see what I'm writing. Otherwise, please complain. So, okay, good. Thank you. Yes, so let's think of the following case. We are looking into transport along a line, along one dimension. Yeah. So we have a this will be our x. Yeah, and we look at a certain position now, and assume that this is, for instance, a thin tube, yeah, and a thin tube and a fluid or a gas is flowing through this thin tube. Yeah, it could also be a pipeline, gas pipeline, or something like that. And now we will look at, into the transport of matter. And let's assume that you have a little chunk of gas, or let's think about one atom of this gas, and this is at this position at time t, and at a later time t plus dt, it will be at another position. Yeah, and what is the metric? What is the thing that we have to take into account if we think about our experience with matter, transport of matter? When we want to move from A to B, we have to walk, or this is the only possibility to transport the matter from A to B is to cross every point that is in between. You know, so in particular, we have to cross this point here. Now, let's say this is position X. There's no way. So there's not a thing like in Star Trek. We don't have beaming. Yeah, so not beam me up. You cannot say beam me up, Scotty. And there's also not a thing like in Harry Potter, apparition, or I don't remember exactly how it's called. Yeah, so you cannot vanish here and show up here. But we have to fulfill this continuity equation condition, that we have to run through every point that is in between. Yeah, that is the idea of the continuity equation. Yeah? So what do we need from that? Yeah, our U, that is the thing that we will have to solve for, is the concentration of a substance at the position X at time t. How can we describe this phenomenon that I just have shown to you? Oops. So I have to get back to my continuity. Yeah. There will also be a flow J of xt, which sorry, it should be located here in the other position. We can assign a flow J of xt that gives us the amount of matter that is transported, or the mass that is transported, or number of particles or mass that is transported over the point X at time t. So the mass per unit time that traverses the position X at time t. And as a convention, you can define it in the other way around, but this is the conventions most people use. If J of X is larger than 0, then the flow is into the right direction, the net flow. Yeah, so particles will move from right to left, and this is J less than 0. Yeah, that would mean particles would move from right to left. Yeah? Larger than 0 means particles are moving from left to right. So now let's consider the mass that we have in a small interval x and x plus delta x. Delta x, for all purposes, or delta x will show up several times. That is just a small space interval, yeah? Or a small number. So now the situation is, we look into this. Here we have x, and here we have another position, x plus delta x. So the width is delta x. And now we consider what mass, what is the change of mass only in this subinterval. Yeah. So let's say we say m is the mass in this interval. So if the delta is small, this will just be the concentration times, and concentration means mass over length, yeah, mass per length, because we are now in a one-dimensional world. In a three-dimensional world, it would be mass per cubic centimeter, for instance, and in a one-dimensional world, it's mass per centimeter. So yeah, so we have the concentration, and we multiply it with the volume or with the length in our case. Yeah. So the mass in this interval will be, to a very good approximation, u, the concentration at time t, and at position x, times delta x. And this means that if we take the change of mass, so when we ask how does the mass in this subinterval change, that will be the time derivative. Yes, the time derivative of u, so the derivative with respect to time times delta x. So, so the change of mass over time, dm over dt. Oh, sorry, I'm not sharing the correct screen. dm over dt. That's du over dt times the size of the interval. And in my notation, this can also be written as ut times delta x. Let me just see. Sorry. In the chat. Okay. So this is one way to put it, but there's another way to express it. And so far, we don't have the idea, made use of the idea that that we have this continuity equation. Everything that so we can express it in a different way. Whenever the mass inside this interval increases, due to continuity, there are only two possibilities. It must cross. If it increases, it must come either from the left side or from the right side, or it can become less. So maybe there's some. It's leaving from the left and from the right side. But whatever it does, every piece of matter that enters this interval has to cross the right or the left border. That is continuity. No beaming, no apparition. Yeah, what does this mean? Yeah, so all mass entering or leaving in the interval must traverse the left or right boundary. Yeah. So how many mass per second will enter over the left boundary? It's J, the mass flow, the flow at the left boundary. And from this, we subtract the flow at the right boundary. This is this one. Why do we subtract it? This is due to our notation. Yeah, think about it. If let's assume there's no flow on the right boundary. So this is 0, and matter is coming from the left boundary. Yeah, which means we have this situation, no flow here. So for some reason it's blocked, and matter is coming in through the right boundary. Yeah. So and then it must increase. Yeah? That's why we have a negative sign, a positive sign at the left boundary. If we make matter leave on the right boundary, because of our convention, then this will be positive as well. Yeah? So on the a positive flow on the left boundary means mass is entering from the left boundary, and the positive flow on the right boundary means mass is leaving from through the right boundary. Yeah, that's why we have this subtraction. So what do we see? We can also express this the same quantity dm over dt, same quantity, by the difference of the flow on the interval boundaries. Yeah, and now, so we have two ways to express this. So, and the only possibility is that this quantity must be the same as this quantity, because both are the same thing, dm over dt. The partial derivative, here I could have used because it's dependent only on one variable. I should have used a d, maybe I will correct that in the slides. So that means we have equality, and now we do the following thing. We rearrange the equation, so divide both sides by delta x, and then we get the differential, this difference quotient. Oh, sorry, I made a typo here, because this is minus. Yeah. So we have a difference, a quotient of a ratio of differences, and this we know in the limit delta x approaching 0. So if this interval size is getting smaller and smaller, this will be just the partial derivative. This will be only one of the things, and the other, this is just the ut must be, due to continuity, the same as so the derivative of u with respect to t must be the same as the derivative of j minus the derivative of j with respect to x. And we can write this in another way, and this is the so-called one-dimensional continuity equation. This looks like a partial differential equation, but actually you would not call this one partial differential, because there are two involved. Yeah? So in a way, it's we have two unknown functions. So what we further need is a relation between u and j, between the concentration and the flow. So, okay, no questions so far. Now let's see what could be useful differential equations that we derive from that. And I will show you three pretty important equations. The first thing, the easiest thing we could think about is there is just a simple proportionality between j and a and u. Yeah, so the first possibility that we consider is that that the flow is just proportional to the concentration. And actually, you can regard this constant a, the proportionality constant. So j and u are unknown functions so far. But a is just a constant, and it's and we can interpret this as a velocity. And if we insert this, J equals A times U, then we can, we just get a linear differential equation of this form. This is the simplest differential equation that we will solve. We will solve it analytically and we will solve it numerically. That's one possibility. Then there's another possibility. It could be that J is not proportional to U, but to the gradient of U, or to the derivative of U. This is done, actually there is a relation like that, yeah, namely Fick's law of diffusion. Yeah, what is the meaning of that? I assume that you have an intuitive feeling about diffusion. What does the diffusion do? Let's assume that we have think of a pipe with a fluid, let's say water, and then we have a sugar concentration in this pipe. Yeah, and let's assume that that at some position you have a pretty high sugar concentration, and at other positions you have a low sugar concentration. What does diffusion do? It will smooth out this function. Yeah. So over time, the sugar concentration will be leveled out. How does diffusion do that? Yeah. So the flow will be high here, and it will be pretty small here. Yeah? It will be high here in this direction, and in order to level out, it will be in the reverse direction. And you can, and Fick's law says it's just the flow is in the reverse direction. That's why there is a minus. And then there's a proportionality constant called the diffusion coefficient. And times du over dx. Yeah, that means the higher the concentration gradient or the derivative is, the higher will be the flux. Yeah, so here we have a here and here we have large absolute values of the derivatives, and here we have a pretty small value. Yeah? So we have slow diffusion here, a small transport here, and a pretty high diffusion, pretty fast transport here. This is Fick's law, and if we enter it into the diffusion equation, we'll find, if you just replace in this continuity equation J with minus du over x, this means that we have take the derivative here of u twice. So this is the famous diffusion equation. The partial derivative with respect to t is d times the diffusion coefficient times the second derivative with respect to u, to x, to the spatial coordinates. And then we can, I will probably, maybe if I have time enough, we can discuss the solution of the diffusion equation, but mostly I will stick to one first order differential equations, because I can demonstrate enough, I think, for starting with partial differential equations on the methods using only first order. So here we had a simple linear proportionality, so a linear relation between J and U. But nobody forces us to have to consider only linear relations, but we can, for instance, take a quadratic relation. And let's assume that the flow is not proportional to u, but to u squared, or to u squared over 2. And this is the so-called inviscid-Burgers equation. That's a non-linear differential equation, and this has some very interesting properties. You can derive some analytical results on it. I will show you how to do this, or indicate this at least. But it's pretty simple, but it also can be used as a kind of toy model for studying nonlinearities. And what is in particular interesting is that the full Burgers equation, that this that's the non-linearity part of it. This is very similar to the NITheCS equations governing fluid flow. Yeah? So this might be your first step towards winning $1 million, studying the inviscid Burgers equation, learn from it, and apply things to NITheCS. Of course, many people have tried, but don't let them discourage you. Yes, so maybe we can look into the NITheCS equation later when we have time enough, but just believe we for one moment. Okay, so we will focus in this lecture on solving this, and we will find something out on solving this, both analytically and numerically. And the method I want to show you, the analytical method, this is called the method of characteristics. And what we will solve is this transport equation here, the continuity equation. So again, it's coming from the continuity equation, and we assume a simple proportionality of the flow with the concentration. By the way, this is also used for not only for gas or heat or something, gas or heat transport, but it could be transport of different things. There are also models for traffic jam. Yeah, there you have the concentration would be cars per kilometer, and the flow would be how many cars can pass a certain position at a time as a parameter. So this is a pretty general setup. You can describe quite a lot of phenomena with that. So now we really want to solve a differential equation, a partial differential equation, and we take this one. Yeah, so this will be our partial differential equation. Let me write it on the whiteboard again. I will do the derivation on the whiteboard, but I wrote it up such that you can use it later for your references. So let's write down the differential equation that we are using. So in full form, it would be du over dt. Plus a. A is a constant, and think of this constant as a velocity, as the transport velocity, times du over dx equals 0. This is the partial differential equation that we want to solve. Yeah. And we want to, u is a function of t and x. This will be interpreted as a time variable, and this is a space variable. And now let's assume that x is just element r. Yeah, so we have an infinite extension. What is t? Yeah, usually we say we are interested in. So we know the situation at one time. Let's get back to the traffic. We know the concentration at one time. Let's say assume we know it at time 0, and we want to predict what is the concentration at a later time. Yeah, so we have an initial condition that specify what is the concentration at time 0. T equals 0, x, and this is a given concentration ux. Yeah, this could be anything. U0 of x. Now, for instance, this could be U0 of x. I don't specify it because it's not necessary. We can make it, keep it very general. Okay, so please ask in the chat if anything is unclear concerning the setup, because I want to have you want you to have some feeling for this. Yeah? So this is our initial condition, and now we ask given this equation, what would be if the flow is governed by this equation? What will be the concentration at a later time? Yeah, and the flow will be the concentration multiplied. So this the flow will look very similar. Flow looks like this, because it's just J. It's A times U0 of X. No? So this will be the that will be the flow at time 0 and position X. Now that we know, it's A0 0X. Maybe you think you can think for a moment. Yeah, so this will be exactly, sorry, should be exactly this exactly proportional. Yeah? Think you for a second if you can imagine what the solution would look like or should look like. Anybody has an idea? Maybe you can write it into the chat if you have an idea what might happen. No problem if you don't have. Okay, now we want to solve this problem. Yeah, and this is done with the so-called method of characteristics. So we have 2 dimensions. And let's say this is the X dimension, the space dimension, and this is the time dimension. And at t equals 0, we have our initial condition. Yeah? So here we have our initial condition. We know the concentration will be U0 of X. Yeah? So this will be a function defined on this red curve. Yeah. So here we have U of at time 0. Here we know the solution. And what we want to know is the solution at a later time. Let's assume that we are here at a later time, at a later position, and we want to know what is the concentration here. And now the idea is that the characteristic this is a contour line. It's a curve in the TX space, along which U is constant. So it's a level curve, yeah, like you know in a map, yeah. So on a map you have seen these levels, yeah. So these are height levels, yeah? So maybe this is a map from a mountain area, and you see that maybe this point is 500 meters above sea level. This is 400 meters, 300 meters, 200 meters, and 100 meters above sea level. Yeah? Maybe it's rather a hill than a mountain. Okay, and we do a similar thing. And the idea here is we have a characteristic. So along this curve, that's a characteristic. And along this curve, the function is constant. Yeah, so this is U on this curve equals a constant. Now, when this is constant, this is a very, very convenient situation, because all we have to do is to run here we want to know the solution at U3x, And all we have to do is follow this curve to the boundary, follow the characteristic to the boundary. And because the function is constant, that means the value here is equal to the value here. Here we are at a position x tilde, for instance. Let's call it. Let me see how I call it in the slides. X prime. I called it x prime. This means that u of tx, all we have to do is follow the characteristic. How we can we'll find the characteristic, I will show you in a second. We follow the characteristics until we hit the boundary. And on the boundary, we know the initial condition. So that will be just ux prime. That's the idea of this story. Okay, so when we have found the characteristics, we have basically solved our problem. We just have to follow the characteristic back. So how can we find the characteristic? So what is the characteristic? Let's assume we can introduce parameters. Yeah. So let's assume a parameter, and let's hope for the situation that we have here. For every time on the characteristic, let's say we have time t, time tau. Let's y tau. Because t is the time where we want to evaluate the function. Yeah, we are interested in t, in the function at position x and at time t. And the characteristic curve that will be, let's call this. Let me stick to the notation here. Yeah. So it's a contour line. So let this be the parameterization. Yeah. So in this case, we have coordinates. The coordinate will be tau and a function psi of psi is the x position. I usually maybe I should write it the other way around first, because here the first coordinate should be. It doesn't matter as long as we know what we are doing. So these are the coordinates of the characteristic. Yeah. So x, psi, tau, tau. Yeah? So at another position, this would be the x psi component. So at given time tau would be the temporal component, and psi of tau, I'm in love with this Greek letter psi, that will be the x component along the characteristic. So the characteristic will be tau. Sorry, I wrote it the other way. Characteristic will be specified by psi of tau. That's the x component in a way, and tau is the y component. Yeah, and the defining condition is that u is constant on the characteristic. So u of psi, tau, and tau is constant on the characteristic. But this means that when it it does not depend on tau. Tau specifies the position on the characteristic at every time. This means that if we take the derivative of a constant with respect to tau, that must be 0. Yeah? Derivative of a constant function is 0. So derivative of psi tau is 0. Yeah, but what is the derivative of psi tau? This is the derivative with respect to the oops, I'm sorry, I'm used the variables the other way around. As I said that the temporal variable comes first. Sorry. Sorry, I have to put this the other way around. Now, what is the time derivative with respect to this one? This is the the multidimensional chain rule that we have to apply. Yes, first we have to take the derivative with respect to the first variable, and this is what we would call the partial derivative with respect to the first variable. So this is du over dt plus, and then there's also an implicit time dependence on the second variable, because we are on we have the second variable, the space variable, in a way depends now on this time on the characteristic, time that we have spent on the characteristic in a way. Yeah? So we have to take the derivative with respect to the space variable, but then multiply it with the inner derivative with d psi over d tau. No, so this would be 0. But on the other hand, our PDE, so this will hold on the characteristic. Holds on the characteristic. At the same time, we know that our PDE, and this looks a little bit, not only a little bit, it looks very similar. Plus A times del U over del X. This holds not only on the characteristic, but this holds everywhere. What does this mean? We have two equations on the this must hold everywhere and also on the characteristics. So on the characteristics, we have to fulfill two equations. Yes. So how can we do this? It holds when this coefficient is equal to A. Yeah. So if d psi over dt equals A. Okay. Yeah. So now we have sorry, d psi over d tau. This is the equation that the characteristic fulfill. That is the equation that the that defines the characteristic. Yeah, but then it's easy to find the to solve this equation. This is a constant. Thereby, we know that psi of tau. This will just be A times tau plus a constant. This is a constant. How can we find this characteristic? Now we are interested in the solution at time t and point x. Yeah? So we know the there are many characteristics, yeah, depending on the niveau line. What is the characteristic that runs through the point tx? Because we don't want to have any contour line. This is a contour line as well. This is a contour line as well. And now actually we know that the contour lines are straight lines. Yeah. So actually we know the contours do not look like this, but these are straight lines. What is the straight line that runs through? We don't want to have the characteristic that runs to any point, but we want to have a characteristic that runs through the point tx. Through tx. This fulfills psi of t, yeah, that's at plus c. This must run, yeah, because at position t, we must be at position, at time t, we must be at position x. And this means that we can find the constant. C equals to, you know, just solve this equation for C. C equals x minus at. And now we have found the characteristic. Yeah, so we have a full characteristic. It's given by that. Yeah, so the characteristic is the full characteristic is let's call this gamma tau. That's psi tau tau. Yeah, and therefore it's second variable is tau, and here we have at plus c, a tau plus c. A tau plus c. And this characteristic, where does this, and we know c equals x minus at. And this, where does this meet the boundary? It meets the boundary at position x prime equals a times 0 plus c. So at a time, and we know the constant. So this is the constant, and this is x minus at. And therefore the solution is u of x t, that's u0 of x prime, and this is u0 of x minus at. This is the solution of our transport equation. Now we have found the analytical solution of this transport equation. As an exercise, you should be able to check this. Let's do this now. Let's see whether we really have a solution. So let's test it. Sorry, there were some messages. Okay, yes. Yeah, right. So let's check the solution. Test the solution. So first, we have to let's see whether the boundary condition is full, or initial condition is fulfilled. Yeah, u of x0, that should be u0 of x minus a times 0, and this is u0 of x. Sorry. So the solution at time 0 at a certain position, this should fulfill the initial condition. Yeah. So if we set the time to 0, like here, we find this is u0 of x, and this means the initial condition is fulfilled. And second thing is, have we fulfilled the PDE itself? Yeah. So ut plus ux, this must be 0 in the end. Yeah? So what is ut? So this is del over dt of u0 x minus at plus del over del x u0 x minus at. Let's see whether this is really 0. Yeah. X u0 is a function of only one variable, so every derivative will be the derivative of x minus at. And now, when we take the derivative with respect to time, we will see that we have to multiply this with a constant minus a. Oh, sorry, I forgot the a here. So ut plus aux. So we have to multiply this with a. I forgot an a here. Plus a times. Yeah? Okay. So this is the first part, and the second part. Yeah? So we have to add a times the derivative with respect to the x variable, and this is u derived at at times the inner derivative is just 1. Yeah? And you see, we have the same values here. Yeah, here we have a with a positive sign. Here we have a with a negative sign. So this sums up to 0, and we have solved our differential equation. Okay, so so far no coding. So the question is, can we solve this using Python? Because we are no coding school here, and actually you can. Python can find the solution for this for you. We can find the same result with SymPy. I will briefly skip through it. How will not talk too much about SymPy. You have seen it. Yeah. So we want to have the symbolic solution. So now we have our constant a, which is the transport velocity. We have x and y. These are oh, actually we don't need y, but we need t. Yeah. And you see, I say I have to tell Python what u is, and I do it this way. I say u is a function of two variables, x and t. I should have written t and x to make it consistent. I can do it. No? So it's a function of two variables, t and x. Ut yeah, that is the derivative with respect to t. Ux is the derivative. Define the differential equation, and this is that these should be 0 by using this terminology. Yeah, you write it as an argument of the equality symbol or equality function. Yeah, so this says the left-hand side should be equal to the right-hand side. Ut plus a times ux must be 0. And then you import from SymPy solver PDE, you import the PDE solve function and solve it, and it's actually the same result that we have. It says you can specify any function, and the solution will be a function of at minus x. We found it's a function, and this is basically the initial condition. You have to that you would have to do for yourself. You have to solve the initial value problem with that. Yeah. So this is a very useful method, and you can check, for instance, your results that you had for solving the differential equation with the characteristic method. So Python can help you with the characteristic method as well. Okay, but one should admit it's you rarely have interesting differential equations that can be solved analytically. Of course, many of the very, very interesting cases can be solved analytically. So you can have nice analytical solution for waves, electromagnetic waves, for instance, or planar waves, or circular symmetric solutions, dipoles, and so on. But in many applications, in particular in fluid dynamics or structural dynamics, you will have to resort to numerical methods. And there's a huge selection of numerical methods, and I will focus, I can only focus on one of them, and these are finite differences. So having solved this our first solution, and by the way, you can solve quite some, definitely not all, but you can solve interesting problems analytically using the method of characteristics. Yeah? So the next more complicated equation may be this. Maybe we can discuss this in the tutorials. But now let's come to the at least equally important, probably more important methods of finite differences. And this is approximating differential equations with finite differences. Yeah. So what we want to do is we want to express our differential equations in terms of finite differences. Yeah? So everywhere, what we can do is introduce a regular grid or grid points and evaluate the function at certain grid points. But at the same time, we have to evaluate the derivatives at certain grid points. Yeah? And so we have to ask ourselves, how can we, when we know the function, how can we find the derivative? And that you know from calculus. You know what the derivative is? It's the limit of the difference quotient by the ratio of the difference. That's in a way the slope of the second. So the limit of the slope f of x plus dx for one-dimensional function, but for if we have multiple derivatives, we will know see what we do. Yeah, so we do this. We have a discretization of time. We have a discretization of space. Yeah, so we have. Let's consider only the space part in this case. Yeah, so let's take f may depend on t, but we have t constant. We keep t fixed. Then we can approximate the derivative with respect to x by the difference quotient. for delta x equal to 0. And what we do is basically we replace everywhere where we have the derivative, we replace it by this approximation here. What is the error that we make? Yeah, so we have equality for the case that delta x, the difference, is approaching 0. But of course, in numerical methods, we have to select a finite delta x. And in order to see what's happening, we have to do a Taylor expansion. So we want to find out what is the relation of f of x plus delta x. So at a different position, at one position, when we know the function at a certain other position. And this is the Taylor expansion. Yeah? And the Taylor expansion to second order looks like this. Yeah? F of x plus delta x is f of x plus the derivative of at position x times delta x plus, then there's a second order correction. And this is taken at a psi, which is somewhere between x and x plus delta x. I hope you have seen this in your math classes. And this is expressed as O of delta x squared. Yeah, so the error, this is the error that you make if you have this linear expansion, so only to first order of delta x, you make an error O of delta x squared. O of delta x squared means that this can be written, this is something smaller than a number times delta x squared. And the number actually is the biggest, so the error cannot be smaller than, not be larger than the biggest value that the second derivative has, the absolute value of the second derivative between x and x plus delta x. So this will be a number. So this error term will be a number between a number. We only have to know that this is a certain finite number. And we make an error of order delta x squared. Now we can rearrange this equation. Yeah? So we have f of x delta x is f of x plus the derivative that we don't know times delta x plus an error that we usually also don't know. We rearrange that for and solve this for f for the derivative, and then we find that the derivative is, not surprisingly, can be approximated by the difference quotient plus the error, which is of order delta x squared divided by delta x. But this means that this is the difference quotient, yeah, this finite ratio plus, oops, oh sorry, I'm in the wrong. Yeah, so if you divide an error of O of delta x squared by delta x, you lose one order. Yeah? So it's an order of error of order first order in delta x. And this is the result that you know. Yeah? If delta x approaches 0, then this error will approach 0 because it's less than finite number times delta x. And if delta x approaches 0, this will approach f of x. Yeah. So we have a first order approximation. This gives us a first order approximation of the derivative. I have an exercise that will be that we will discuss in the tutorials. Now let's come to the finite difference solution of a PDE. Then we do the same trick. Now we introduce a regular grid. So now we want to solve that equation that we just have seen. Yeah, the same equation that we have solved analytically. We have an initial condition. I called this U0. Now I call this f of x. Yeah? And because we cannot have an infinite interval for all practical purposes, so we restrict ourselves to a finite interval. And let's assume what happens if the function is transported via the left or right boundary of the intervals, let's just assume that we have a finite periodic boundary condition. So everything that vanishes on the left boundary, right boundary enters back by the on the left boundary. And now we introduce a finite an equidistant grid. Yeah, so do it like this. Yeah, okay, I see in the chat, the slides are not the same as those in the notes. The slides that you can download were an earlier version. I will give you an updated version at the end of the day latest. Yeah. So they are not exactly the same, but pretty close. Okay, so here we have our interval from 0 to L, and now we do finite steps. So here we have a point x. Here we have x plus delta x, and here we have x minus delta x. Yeah? So we have same distance, and that's what we call a regular grid. Yeah? So the width of the grid is everywhere the same. That's there are other methods, but we take this method, and we assume a regular grid. Yeah, so this. So what is delta x? This is just L divided by N. And we do the same with the time coordinate. Yeah? So we also introduce in time a regular grid. So let's say we have a width delta t. Delta t. So here we start at 0. And here we are at delta t, here we are 2 delta t, and so on, until we reach the time t equals to, let's say, capital T. And now what we do is so we are interested only at these grid points. Yeah? So for instance, at this would be the point x position 3 times delta x and 2 times delta t. Yeah. So we discretize the function. We say u and k. K is the time step. It doesn't mean to the power of k in this case, but it means we are in the kth time step, and we are on the nth grid point in space. Now, kth grid point in time, nth grid point in space. And now we do our finite difference approximation. First, with respect to time, this means we move 1 time step ahead. So we approximate it in time. That is a forward difference quotient. A forward finite difference. Yeah, so this is an approximation of the derivative with respect to time. Yeah? So we are at the same position, we keep the position constant, and look at the solution 1 time step later and 1 time step at the current time step. Yeah, and for the spatial derivative, we say time is constant. So we look at it at, oh, sorry, I make it a mistake here. Sorry, kn. Yeah, so we are interested at time step t. Time step k. We want to know the finite. We want to know the derivative, and there we take a backward derivative for reasons that I will tell you later. We take a backward derivative. And now we say this is equal. This equals to one another, and then this gives us a method. Yeah, but when I will write down what are the equations. So the equations ut plus a times ux. We approximate ut equals, or let's do it this way. Ut at the kth at time step k times delta t, and at position n times delta x. Yeah. So again, u k times delta t, n times delta x. This is what we have called ukn. Yeah. And we say this is approximately equal if we neglect the order, the error term. This is the difference in time means u k plus 1, you make one step ahead, minus same position, fixed position n, and you take the difference and divide it by delta t. So same with the ux, k delta t. And delta x. You approximate this as u k minus uk. Yeah, so you keep time fixed, but you vary now the spatial position. We could do one thing. One thing we could do, we could also take a forward difference. Then this would be un minus un minus 1. Un plus 1 minus un. But actually, it turns out, and I will show you the reason why. It turns out that in this case, it's better to take a backward difference divided by delta x. This is called an upwind scheme. Yeah. So and now we plug this into this differential equation that this should be 0. And we get the system. We get as an equation uk plus 1 n minus ukn divided by delta t plus a times ukn minus ukn minus 1 divided by delta x. This equals 0. And this now allows us, and this is to solve for uk plus 1. So we rewrite this. So we get uk plus 1 at position n equals, we can get this from the previous time step. Yeah. So how can we get it? If we solve it, it's the position at the previous time step. We multiply this with delta t, and then we get plus a times delta t over dx, delta x, we call this sigma, times this value ukn minus ukn minus 1. Yeah, so this is and this is an equation that that we can use to find what we know is the initial condition. Yeah, so we know the solution at u0n. Find the solution using this recursion, and we can go to the second time step, and then we go to until we are finished. Yeah? So let's say after m iterations, that may be that is the time that we are interested in. Yeah. So this is the forward solution scheme, an explicit solution scheme. So that means we can solve the PDE numerically by taking the initial condition and updating the function with, oh, okay, sorry, I just see that I made introduced the wrong sign. Yes, so we have an a here. We bring this to the right side of the equation. So this is the minus. Yeah, so this is our iteration. We start at the boundary at the initial condition, and then we find the new solution by just updating these steps. And let's do it now. So what do we do? I have introduced some value. I've introduced a grid with grid size 200. So this is the solution at time t that will be a 200 a vector of length 200. The length, I said it's arbitrary value. I just said it's 30. Yeah, so the length of the system is 30. dx then is the length divided by the number of steps that we have. The velocity, this transport velocity, is 1, and I introduced. I didn't say what is the relation between the time step and the step that we make in the time direction and the step that the grid size. Let's assume these are the same for the moment. We will get rid of this assumption, but let's assume for the moment that these are the same. And we will store the solution. Yeah, okay. This is the representation of the x values, and let's assume that we have a Gaussian function. So this will be a Gauss curve centered at position 5. And now, we have the sigma specified by a times dt over dx. We start at position at time 0, and my plan is, so this u0, this is the initial condition. Yeah, so we start with the peak at position 5. This will be a Gauss function, and then we see what will happen. And we will evolve in time until we have reached the time 1. So we start at set the timer at time 0, and now we start with the iterations. So we know the solution at time 0. Now we want to have the solution at time t, and we just have to see what do we have to do. We have the solution at the previous time